The main components that make up an automatic transmission include planetary gear sets, which are the mechanical systems that provide the various forward gear ratios as well as reverse. The hydraulic system, which uses a special transmission fluid sent under pressure by an oil pump through the valve body to control the clutches and the bands in order to control the planetary gear sets. Seals and gaskets are used to keep the oil where it is supposed to be and prevent it from leaking out. The torque converter, which acts like a clutch to allow the vehicle to come to a stop in gear while the engine is still running. The governor and the modulator or throttle cable monitor speed and throttle position in order to determine when to shift. The computer, which controls shift points on newer vehicles and directs electrical solenoids to shift oil flow to the appropriate component at the right instant. Planetary gear sets. Automatic transmissions contain many gears in various combinations. In a manual transmission, gears slide along shafts as you move the shift lever from one position to another, engaging various sized gears as required in order to provide the correct gear ratio. In an automatic transmission, however, the gears are never physically moved and are always engaged to the same gears. This is accomplished through the use of planetary gear sets. The basic planetary gear set consists of a sun gear, ring gear, and 2 or more planet gears, all remaining in constant mesh. The planet gears are connected to each other through a common carrier, which allows the gears to spin on shafts called pinions, which are attached to the carrier. One example of a way that this system can be used is by connecting the ring gear to the input shaft coming from the engine, connecting the planet carrier to the output shaft, and locking the sun gear so that it can't move. In this scenario, when we turn the ring gear, the planets will walk along the sun gear, which is held stationary, causing the planet carrier to turn the output shaft in the same direction as the input shaft, but at a slower speed, causing gear reduction, similar to a car in first gear. If we unlock the sun gear and lock any 2 elements together, this will cause all 3 elements to turn at the same speed, so that the output shaft will turn at the same rate of speed as the input shaft. This is like a car that is in third or high gear. Another way that we can use a planetary gear set is by locking the planet carrier from moving, then applying power to the ring gear, which will cause the sun gear to turn in the opposite direction, giving us reverse gear. The illustration on the right shows how the simple system described above would look in an actual transmission. The input shaft is connected to the ring gear, dark gray. The output shaft is connected to the planet carrier, light gray, which is also connected to a multi-disc clutch pack. The sun gear is connected to a drum, orange, which is also connected to the other half of the clutch pack. Surrounding the outside of the drum is a band, blue, that can be tightened around the drum when required to prevent the drum with the attached sun gear from turning. The clutch pack is used, in this instance, to lock the planet carrier with the sun gear, forcing both to turn at the same speed. If both the clutch pack and the band were released, the system would be in neutral. Turning the input shaft would turn the planet gears against the sun gear, but since nothing is holding the sun gear, it will just spin free and have no effect on the output shaft. To place the unit in first gear, the band is applied to hold the sun gear from moving. To shift from first to high gear, the band is released and the clutch is applied, causing the output shaft to turn at the same speed as the input shaft. Many more combinations are possible using 2 or more planetary sets connected in various ways to provide the different forward speeds and reverse that are found in modern automatic transmissions. Some of the clever gear arrangements found in 4 and now 5, 6 and even 7-speed automatics are complex enough to make a technically astute layperson's head spin, trying to understand the flow of power through the transmission as it shifts from first gear through top gear while the vehicle accelerates to highway speed. On newer vehicles, the vehicle's computer monitors and controls these shifts so that they are almost imperceptible. Clutch packs. A clutch pack consists of alternating discs that fit inside a clutch drum. Half of the discs are steel and have splines that fit into grooves on the inside of the drum. The other half have a friction material bonded to their surface and have splines on the inside edge that fit grooves on the outer surface of the adjoining hub. There is a piston inside the drum that is activated by oil pressure at the appropriate time to squeeze the clutch pack together so that the 2 components become locked and turn as one. One-way clutch. A one-way clutch, also known as a Sprague clutch, is a device that will allow a component such as ring gear to turn freely in one direction but not in the other. This effect is just like that of a bicycle, where the pedals will turn the wheel when pedaling forward, but will spin free when pedaling backward. A common place where a one-way clutch is used is in first gear when the shifter is in the drive position. When you begin to accelerate from a stop, the transmission starts out in first gear. But have you ever noticed what happens if you release the gas while it is still in first gear? The vehicle continues to coast as if you were in neutral. Now shift into low gear instead of drive. When you let go of the gas in this case, you will feel the engine slow you down just like a standard shift car. The reason for this is that in drive, a one-way clutch is used whereas in low, a clutch pack or a band is used. Bands. A band is a steel strap with friction material bonded to the inside surface. One end of the band is anchored against the transmission case, while the other end is connected to a servo. At the appropriate time, hydraulic oil is sent to the servo under pressure to tighten the band around the drum to stop the drum from turning. Torque converter. On automatic transmissions, the torque converter takes the place of the clutch found on standard shift vehicles. It is there to allow the engine to continue running when the vehicle comes to a stop. The principle behind a torque converter is like taking a fan that is plugged into the wall and blowing air into another fan which is unplugged. If you grab the blade on the unplugged fan, you are able to hold it from turning, but as soon as you let go, it will begin to speed up until it comes close to the speed of the powered fan. The difference with a torque converter is that instead of using air, it uses oil or transmission fluid, to be more precise. A torque converter is a large donut-shaped fluid coupling, 10 to 15 in diameter, that is mounted between the engine and the transmission. It consists of three internal elements that work together to transmit power to the transmission. The three elements of the torque converter are the pump, the turbine, and the stator. The pump is mounted directly to the converter housing, which in turn is bolted directly to the engine's crankshaft and turns at engine speed. The turbine is inside the housing and is connected directly to the input shaft of the transmission, providing power to move the vehicle. The stator is mounted to a one-way clutch so that it can spin freely in one direction, but not in the other. Each of the three elements have fins mounted in them to precisely direct the flow of oil through the converter. With the engine running, transmission fluid is pulled into the pump section and is pushed outward by centrifugal force until it reaches the turbine section, which starts it turning. The fluid continues in a circular motion back towards the center of the turbine, where it enters the stator. If the turbine is moving considerably slower than the pump, the fluid will make contact with the front of the stator fins, which push the stator into the one-way clutch and prevent it from turning. With the stator stopped, the fluid is directed by the stator fins to re-enter the pump at a helping angle, providing a torque increase. As the speed of the turbine catches up with the pump, the fluid starts hitting the stator blades on the backside, causing the stator to turn in the same direction as the pump and turbine. As the speed increases, all three elements begin to turn at approximately the same speed. Since the 80s, in order to improve fuel economy, torque converters have been equipped with a lock-up clutch, not shown, which locks the turbine to the pump as the vehicle speed reaches approximately 45 to 50 miles per hour. This lockup is controlled by computer and usually won't engage unless the transmission is in third or fourth gear. Hydraulic system. The hydraulic system is a complex maze of passages and tubes that sends transmission fluid under pressure to all parts of the transmission and torque converter. The diagram at left is a simple one from a 3-speed automatic from the 60s. The newer systems are much more complex and are combined with computerized electrical components. Transmission fluid serves a number of purposes, including shift control, general lubrication, and transmission cooling. Unlike the engine, which uses oil primarily for lubrication, every aspect of a transmission's functions are dependent on a constant supply of fluid under pressure. This is not unlike the human circulatory system. The fluid is even red, where even a few minutes of operation when there is a lack of pressure can be harmful or even fatal to the life of the transmission. In order to keep the transmission at normal operating temperature, a portion of the fluid is sent through one of 2 steel tubes to a special chamber that is submerged in antifreeze in the radiator. Fluid passing through this chamber is cooled and then returned to the transmission through the other steel tube. A typical transmission has an average of 10 quarts of fluid between the transmission, torque converter, and cooler tank. In fact, most of the components of a transmission are constantly lubricated in fluid, including the clutch packs and bands. The friction surfaces on these parts are designed to operate properly only when they are coated in oil. Oil pump. The transmission oil pump, not to be confused with the pump element inside the torque converter, is responsible for producing all the oil pressure that is required in the transmission. The oil pump is mounted to the front of the transmission case and is directly connected to the hub of the torque converter housing. Since the torque converter housing is directly connected to the engine crankshaft, the pump will produce pressure whenever the engine is running, as long as there is a sufficient amount of transmission fluid available. The oil enters the pump through a filter that is located at the bottom of the transmission oil pan and travels up a pickup tube directly to the oil pump. The oil is then sent under pressure to the pressure regulator, the valve body, and the rest of the components as required. Valve body. The valve body is the control center of the automatic transmission. The valve body contains a maze of channels and passages that direct hydraulic fluid to the numerous valves, which then activate the appropriate clutch pack or band servo to smoothly shift to the appropriate gear for each driving situation. Each of the many valves in the valve body has a specific purpose and is named for that function. For example, the 2 to 3 shift valve activates the second gear to third gear upshift, or the 3 to 2 shift timing valve, which determines when a downshift should occur. The most important valve, and the one that you have direct control over, is the manual valve. The manual valve is directly connected to the gear shift handle and covers and uncovers various passages, depending on what position the gear shift is placed in. When you place the gear shift in drive, for instance, the manual valve directs fluid to the clutch packs that activates first gear. It also sets up to monitor vehicle speed and throttle position, so that it can determine the optimal time and the force for the 1 to 2 shift. On computer-controlled transmissions, you will also have electrical solenoids that are mounted in the valve body to direct fluid to the appropriate clutch packs or bands under computer control to more precisely control shift points. Computer controls. The computer uses sensors on the engine and transmission to detect such things as throttle position, vehicle speed, engine load, stop light switch position, etc. to control exact shift points, as well as how soft or firm the shift should be. Some computerized transmissions even learn your driving style and constantly adapt to it, so that every shift is timed precisely when you would need it. Because of computer controls, sports models are coming out with the ability to take manual control of the transmission as though it were a stick shift, allowing the driver to select gears manually. This is accomplished on some cars by passing the shift lever through a special gate, then tapping it in one direction or the other in order to upshift or downshift at will. The computer monitors this activity to make sure that the driver does not select a gear that could overspeed the engine and damage it. Another advantage to these smart transmissions is that they have a self-diagnostic mode, which can detect a problem early on and warn you with an indicator light on the dash. A technician can then plug test equipment in and retrieve a list of trouble codes that will help pinpoint where the problem is. Governor, vacuum modulator, throttle cable. These 3 components are important in the non-computerized transmissions. They provide the inputs that tell the transmission when to shift. The governor is connected to the output shaft and regulates hydraulic pressure based on vehicle speed. It accomplishes this using centrifugal force to spin a pair of hinged weights against pullback springs. As the weights pull further out against the springs, more oil pressure is allowed past the governor to act on the shift valves that are in the valve body, which then signal the appropriate shifts. Of course, vehicle speed is not the only thing that controls when a transmission should shift. The load that the engine is under is also important. The more load you place on the engine, the longer the transmission will hold a gear before shifting to the next one. There are 2 types of devices that serve the purpose of monitoring the engine load: the throttle cable and the vacuum modulator. A transmission will use one or the other, but generally not both of these devices. Each works in a different way to monitor engine load. The throttle cable simply monitors the position of the gas pedal through a cable that runs from the gas pedal to the throttle valve in the valve body. The vacuum modulator monitors engine vacuum by a rubber vacuum hose which is connected to the engine. Engine vacuum reacts very accurately to engine load, with high vacuum produced when the engine is under light load and diminishing down to 0 vacuum when the engine is under a heavy load. The modulator is attached to the outside of the transmission case and has a shaft which passes through the case and attaches to the throttle valve in the valve body. When an engine is under a light load or no load, high vacuum acts on the modulator, which moves the throttle valve in one direction to allow the transmission to shift early and soft. As the engine load increases, vacuum is diminished, which moves the valve in the other direction, causing the transmission to shift later and more firmly. Seals and gaskets. An automatic transmission has many seals and gaskets to control the flow of hydraulic fluid and to keep it from leaking out. There are two main external seals, the front seal and the rear seal. The front seal seals the point where the torque converter mounts to the transmission case. This seal allows fluid to freely move from the converter to the transmission, but keeps the fluid from leaking out. The rear seal keeps fluid from leaking past the output shaft. A seal is usually made of neoprene, similar to the neoprene in a windshield wiper blade, and is used to keep oil from leaking past a moving part such as a spinning shaft. In some cases, the neoprene compound is assisted by a spring that holds the neoprene in close contact with the spinning shaft. A gasket is a type of seal used to seal two stationary parts that are fastened together. Some common gasket materials are paper, cork, rubber, silicone, and soft metal. Aside from the main seals, there are also a number of other seals and gaskets that vary from transmission to transmission. A common example is the rubber O-ring that seals the shaft for the shift control lever. This is the shaft that you move when you manipulate the gear shifter. Another example that is common to most transmissions is the oil pan gasket. In fact, seals are required anywhere that a device needs to pass through the transmission case, with each one being a potential source for leaks. Components of a transmission. 1. Transmission case. The outer shell that houses the internal components of the transmission. It provides protection and helps maintain the necessary lubricant inside. 2. Torque converter. A fluid coupling that allows the engine to spin independently of the transmission. It provides a smooth transition of power and enables the vehicle to stop without stalling the engine. 3. Planetary gear set. The heart of the automatic transmission, comprising gears that allow for different gear ratios. This set includes the sun gear, planet gears, and ring gear, facilitating smooth shifting between gears. 4. Clutch packs. Used in automatic transmissions to engage and disengage various gears. When activated, these packs allow for a smooth transition between gears without manual intervention. 5. Valve body. A complex system of channels and passages that controls the flow of transmission fluid. It directs fluid to the various clutches and bands within the transmission to facilitate shifting. 6. Output shaft. Connects to the drive shaft, transferring power from the transmission to the wheels. 7. Shift linkage. The mechanism that connects the gear shifter in the cabin to the transmission, allowing the driver to select different gears. 8. Transmission fluid. A vital lubricant that cools and cleans the internal components while providing hydraulic pressure necessary for operation. 9. Sensors and control module. Modern transmissions often include electronic sensors and a control module that monitor various parameters to optimize shifting and performance.